And so I'm going to talk about, change gears a little bit and talk about our research that we're doing in the Department of Chemical Engineering on solar photovoltaics and next generation materials and devices that could play a key role in solving a lot of our climate issues. I'm a chemical engineer, so I'm going to give just a very brief perspective from a chemical engineering perspective. But I am a physicist by background, and I think that gives a good example of how interdisciplinary the department is. Essentially, I mean, chemical engineers, we convert raw materials into useful things, and that takes many different forms. That can be anything from healthcare, from drugs, through to chemical products, through to new energy systems. And it really sits at the interface between pure science and engineering. Those of you who are interested in both, this chemical engineering could be very much of interest to you. And we are trying to solve real world problems at scale. So really thinking about scaling things up. The department here in Cambridge has a big theme around sustainability and energy. And so that's what the topic of the talk today will be. So I'm going to talk particularly about, I hope you can see, I'm going to use my pointer down here. I'm going to talk particularly about solar photovoltaics and some of the work we're doing around that. So first of all, just to give some context of how much solar power there is out there. If this cube represents how much sunlight's hitting the Earth at any one time, then this is our global power demand. So you can see solar has a huge potential to provide absolutely everything we need to power everything we need to power. But of course, this is our current, this tiny speck there on the right represents our current PV installations. So we're just under a terawatt. It's actually a lot installed, but we still have a long way to go to be able to match what we need in terms of the global power demand. What's really exciting though is that solar PV and solar photovoltaics are being deployed very fast. We are seeing lots more solar being installed, and you're probably seeing this on rooftops and on buildings and solar farms around the country and around the world. This is fantastic. This is what we need to be tackling big climate issues. This plot here is showing that each year the International Energy Agency predicts how much solar will be deployed. And so these are these dashed lines here. This is every year they make a prediction and projection out to what will be installed. And then these black points here actually show what is actually installed. And you can see year after year consistently that IEA is under predicting how much solar is going to be rolled out. So we are putting more and more in line than we could have even predicted, or that we could have even imagined. And a lot of this is because the prices come down so much. So if we think about the cost of solar power, so here we usually think in terms of dollars per watt. So how much power, so how much it costs to produce each electrical watt. It's dropped a huge amount. So it's dropped a factor of 100 times since 1980. So you can see this plot here over the years. And another 10 times even just since 2010, which is absolutely amazing. It's something we could not have predicted coming in even a decade ago. And a lot of this is because of cost reductions. So a lot of it's in economies of scale, so cost reductions in the raw materials and the manufacturing, but also just in good science and good engineering, producing power conversion efficiency gains. So these solar panels are getting more and more efficient. And the technology we have on most rooftops, or that you will see mostly around, is crystalline silicon. This is the dominant market share. It's around 90% of the market share is with this technology. It is very good. It's a very good technology. It will last on your rooftop for 30 years. So it is, and it is one of the reasons why we have so much solar installed today. But the problem is silicon can't take us the whole way there. It will fall short in the long run. It can't take us all the way from this 1 terawatt we have now all the way to 20 terawatts plus that we will need. And there's a few reasons for this. One is that in a solar system, it's not just the panel that costs money. It's the wiring, the installation, the inverter as well, because you're producing DC power. We need to convert that back to AC power to make it useful. And so there's these what's called balance of systems costs, these BOS costs, which are now starting to dominate the cost of a solar installation. So this plot is showing that the cost of the module on German rooftop systems, which has really come down in price a lot over the last decade, and in fact will continue to come down in price. But then there's these balance of systems costs, which are starting to dominate. In fact, as we go out further and further, these costs will be absolutely dominant. And it's very hard to make these less expensive unless we can make the cells more efficient. The panels are typically bulky and rigid, so that you see them on the rooftops. They're quite heavy and complicated to install. You have these racks on rooftops that mean you need several people installing them, and it's quite complicated infrastructure. So it doesn't have, we don't have much flexibility in what we can do and where we can put the solar. And finally, just the cost of producing it is also quite high, and therefore the cost to produce a factory, to make a factory and to scale many factories is quite high. And this is fundamentally because with silicon, we have to heat it to very high temperature to get rid of defects and impurities. And so that means it limits how fast we can build factories and therefore how fast we can install more and more solar. And so what we need is solutions that have higher efficiency, more modularity, so we can do more things with it than just the rigid panels. And this will drive the cost of electricity from solar down further and accelerate meeting the climate goals. So to give just a very brief overview of what a solar cell is and how it works. So what we have is in its essence, it's quite a simple structure. We have something on, for example, a glass substrate, and then a transparent anode, and then the light shines through that device, and then there's an absorber layer that then absorbs the light and energizes electrons, which we then collect at the electrodes. It doesn't just energize electrons, it also leaves behind what's called a hole, which is where the electron was. And we actually have to think about that charge, a hole, moving as well. And some of you will have come across holes before, some of you will not have. And so here, so for example, when we shine light on, we energize these electrons and holes, and we transport them to the opposite electrodes. And so that what we need for an efficient solar cell material is we need that material to absorb light as well as possible, and then transport those charges really well to the electrodes. So I'm going to play that one more time here. So we generate these electrons and holes that energize and collected, and then they drive a current around an external circuit. Okay, so one of the materials that we're working with, they're called Halide Perovskites, and these are it's a material it's an ionic material, and it takes the crystal structure ABX3. That's what a perovskite crystal structure is. And there are many natural minerals of perovskite found in the earth. These particular ones we're working with for solar cells are man-made ones. They have components that we have to make in the lab, but they're very simple to make. We typically have different salts and metal halide salts and organic salts that we mix together to make these crystals. And the reason they're creating a lot of excitement is because they're making very efficient solar cells. And so this is showing the efficiency of the solar cells over the years, over the last 30 or 40 years. And you can see silicon here, which is essentially the workhorse system, is at about 26.6%. The perovskite is already up, approaching that, and probably will overtake it very soon. And this is extremely exciting because it is a new material that really has done this just over a decade of development. And the other really exciting thing about it is that we can make it very inexpensive. Into inks, and we deposit them down onto these glass substrates, and then, so for example, we on these glass substrates we might spin them very fast, and that makes a very uniform film, which is this yellow film here. And then we heat it quite gently. So 100 degrees Celsius is a very gentle heating for semiconductor processing. It forms this really nice crystalline film. It's a very dark absorbing film. Because we can do this at quite low temperature, it means we can actually think about processing like newsprint. We can think about roll-to-roll processing of these solar cells. You can just think about how we make print newspapers. We can do the same thing for solar cells. And you can just imagine just how fast we can make those panels and how fast we can make those solar cells. And this is actually an example prototype roll-to-roll line where we have the material before it's heated and then the material after it's heated. And this is on a plastic foil, so we don't have to do it on glass. And this opens up more versatile processing. And in fact, because we can do it on plastic, we can think also about flexible and lightweight solar panels. This is very much a paradigm shift from what we think about as a solar panel on a rooftop. So that's one shown here. So you can think about clothing that has solar panels built in. We can think about rooftops where we can just roll the panels out like tarps on the rooftop. And this has much cheaper. This will be much cheaper to install. We can also think about applications where you need very high power to weight ratios. So space applications and other aerial vehicles, which are becoming more and more important for aerial communication, and also electric vehicles. So boosting the range of electric vehicles. So this is something where we don't want to add weight to the car, but we do want to generate power. So a very lightweight solar panel is very important here. We can also think about colored solar cells as well. So we can make these perovskite films with different colors. So not just the really dark films, but we can tweak the composition and the contents to change the band gap. So we change the color it absorbs. And so we can think about actually designing these cells and modules into the buildings. So rather than thinking about hiding them on the rooftop, we can actually build them into the building facade. And because we can change the color of these cells, what we can actually do is we can layer two cells together that absorb slightly different colors of the solar spectrum. So they're shown in this diagram here. So this top cell is harvesting the bluer wavelengths, so the UV and the blue, and then the redder wavelengths actually pass through and are absorbed by the cell below it. And so this is what's called a tandem solar cell. And because we're harvesting complementary regions of the spectrum, we can actually push the efficiency beyond silicon and beyond some of the limits that we have for solar cells today. So for example, silicon is projected can reach about 28% efficiency. These tandems can reach 35%. And this doesn't sound like much. It doesn't sound like much of an improvement of efficiency, but if it's operating for 30 years, producing power for that whole time, it's a huge amount of energy gain, and therefore the cost of that electricity has come down really quite dramatically. So this actually is a very important improvement in performance. We can also think about putting the perovskite on top of silicon, so on top of the existing technology. So tandem actually together with the silicon, and that has some advantages because you can think about taking the current technology and boosting it and making it better. And it's quite an exciting time for these materials. They're just coming into commercialization now. So this year, the first production lines have started rolling out. The first pilot lines and even production lines are coming out. There's so Oxford Photovoltaics, for example, a company out of Oxford producing some modules, and there's a few others in the US and in China as well. So it really is an exciting time to see this technology that's really being developed in the labs to now be pushing now into commercial production and really starting to make an impact on energy generation. But of course there are challenges, and I just want to finish the last part of my talk talking about the challenges to scaling this up. So the job isn't done. We do need to still solve problems. One of them is, how do we take the efficiencies to these limits, or to and above the traditional limits? I talked about this 35% target. There's still some way to go to get to that. And so we do need to keep working on how to make these materials more efficient. How do we scale them up to larger cells and modules? Typically in the lab, we use sort of quite small cells that are one inch square just for prototypes, but we need to make them scale them up to either mini module or even a large module size, which is more like a meter squared. So there's a challenge in depositing the materials and making them uniform enough and high performing enough across that whole module. And then finally, how do we make it last for 30 years? When you buy a silicon panel now, you have a warranty that will say it will last for at least 30 years. So it's a very high mark set, but it does mean we do need to make these cells stable and make them last on a rooftop. So this is my research group. This is us at Clare. Of course, this was taken before the pandemic, so we could still meet. This is what we look like today at the moment on Zoom. Of course, we're hoping that will change very soon. We'll be able to meet all in person again. But we are a very interdisciplinary bunch. So we're in the chemical engineering department, but we're also physicists, chemists, material science, and electrical engineers. I think that gives a good flavor for what we do in chemical engineering that really does span across many, many different disciplines. And one of the particular things we do is we use laser spectroscopy to understand these materials. So we excite these materials with packets of lasers, or very fast pulse of lasers, laser light, and then we look at how fast those excited charges decay away. And that tells us a lot about if these charges trap, how much current we can produce in the cells, and various other loss processes as well. So it tells us a lot of information about what's happening inside the cell that we wouldn't know without using these tools. And so just to give one or two examples of what we do, this is actually, we look at, in a microscope, we can actually put these lasers through a microscope and actually look at where these losses are on the micro scale. So you can see the scale bar here, this is 2 micrometers, so a millionth of a meter. So we're really looking at very, very small features here. And so these materials, they're made of, you can see that they're made of grains. So it's kind of like a mosaic of grains. And what we find is some of these grains are really, really poorly performing. And this is what we do is here, we're shining the laser and we're looking at the light coming out. And the light coming out tells us about whether there's traps in the material. So where we see not much light coming out, it means a lot of those energized charges are actually being trapped and they lose their energy to heat. So here you can see these dark regions here, we have lots of power losses in this solar cell, but then some of these bright regions here, this is very good and they perform very well. So we're trying to understand why there's some regions are dark and some regions are really light. And we've also been working on ways to treat these films and actually make them better. And you can see this is one example here where we've been looking at different additives and different post-treatments to the films, and you can see it's much more uniform in terms of its spatially across the film, but also it's also much more luminescent and much brighter. So in doing this, we've gotten rid of a lot of these defects and a lot of these traps that were there in the film. Another challenge I mentioned was trying to scale them up to large area. I mentioned how we take these substrates and we spin coat on them. So we put down some solution and we spin them really fast. That's okay in the lab, but it's not scalable. We can't have a huge spin coater that spins things really fast. So actually what we've been looking at is different vapor deposition techniques where we actually thermally evaporate. So we actually sublime the materials. So they're powders and then they sublime onto the film. We heat those powders and they form these thin films on the substrate. And they form very, very uniform thin films. So this is a very good technique for producing, and you can see here this is on a flexible plastic. You can get really nice uniform films in this way, and particularly over large area. And the final thing I wanted to mention was long-term operation. How do we make them last on the rooftop for 30 years plus? And so one thing, they need to pass many industry standard tests, so thousands of hours at very high stress conditions. So we do a lot of tests where we run the cells under these industry standard tests. So there's things like the damp heat test where we actually expose them to very high humidity and very high temperature. So they're at something like 85% humidity and 85 degrees Celsius for some time, and we operate them and we see how long they can last under those conditions. We also do things like temperature cycle from very high temperature to low temperature and back up. And we need to check even in these very high stress conditions that they pass these tests, and therefore they're ready for the next applications. And so this is an example, some data where we look over many hours and looking at the efficiency, which is in red here. And you can see actually this is a cell that is very stable. So over 2,000 hours, which is several months, it is operating very well, even at very high temperature, which is very promising. And we've also been doing a lot of measurements looking at testing their radiation hardness for space. So we actually bombard these cells with high energy protons to see if they survive, and they do. These perovskite materials are actually very stable and tolerant to a lot of these high energy radiation, which is very promising for space applications. One thing is that failure mechanisms need to be better understood, and this is very much a key engineering challenge. How do we understand where these cells fail and how do they fail? How do we stop them from failing as well? And this is a big topic going forward. And also module and packaging developments. How do we ensure that we can package these, protect them from the elements, protect them from oxygen, from rain, from other things, to ensure reliable operation. So with that, I'm going to sum up that we, and just to show, I've shown some of the research we're doing in the chemical engineering department, and particularly we're looking at trying to make these perovskite cells that are very expensive to be high performing and to last on the rooftop. There are some challenges still remaining, of course, and that's topics of ongoing research that will continue. But I do hope that you'll be seeing a lot of these cells on rooftops very soon. So thank you very much.